Hello. So far we have discussed about the cyclic coordinates and how identification of cyclic coordinates helps us to understand the hidden conservations. We concluded that if any coordinate qk is absent in the Lagrangian of a given system, we call that coordinate as a cyclic coordinate, with the consequence that the conjugate momentum of that coordinate will be a conserved quantity. Now, in this session, we will try to relate symmetries with the underlying conservation laws. Maybe you know as a physics student that symmetries play a major role in understanding the physical nature of systems, and it's by some arguments based on the symmetries we are able to advance much in particle physics. Especially the symmetry of particle families helps us to predict many members of those family which were hidden, and you will also learn much in detail about these symmetries in your postgraduate courses as well. So anyway, let me just give an introduction about the symmetries and associated conservation laws. Unfortunately, our university syllabus does not mention anything about this particular topic, but you will see that this particular topic is of utmost relevance whenever you go to your modern physics, quantum mechanics or nuclear physics, where you will understand that related to every symmetry of the system you can find out a conservation law, and knowing or understanding the relation between the symmetries and the associated conservation laws will help you to appreciate how those scientists were able to make such successful predictions about hitherto unknown particle families, especially in particle physics. Now let me begin with the simplest cases. This is all just as an introductory remark. I won't spend much time on this symmetries and conservation laws, but it's only just for completing our to give completeness to our course. I'm just adding this one. I'll give you some references which will be of use for you. If you can spend time on it, it will add on to your knowledge. See, suppose that we will talk about three types of invariance. We will talk about three types of invariance. One is known as translational invariance. Symmetry is related to what is known as invariance, right? If certain quantities are changed, if the system doesn't show any change, any notable difference, we say that the system is remaining what? Invariant. Or we'll say that the system is possessing certain types of what? Symmetry, right? Left-right symmetry, mirror symmetry, you have if you have studied chemistry, you would have learned about what is known as the chirality, right? The mirror symmetry and all, right? You'll talk about more symmetry in physics later when you study about the group theory and all. So suppose that if the Lagrangian of the system is invariant, right? If the Lagrangian of the system, I'm talking in terms of the Lagrangian, that's better. You know that the Lagrangian of the system is a well-behaved function which carries all information regarding the dynamics of the system. If you know the Lagrangian of the system, from the Lagrangian of the system, you can just drive out, or you can just drain out, all necessary information. That is a belief. That's a wonderful function that we have regarding a system. So if the Lagrangian of the system is invariant, if the Lagrangian of the system is invariant means it remains the same, it's not affected. Invariant when the origin of the coordinate system is changed. Origin of the coordinate system, you know that Lagrange is a function of coordinates, of the origin of the coordinate system. We may be using any suitable coordinate, Cartesian coordinate or polar coordinates, whatever it is. Origin of the coordinate system is changed we can say that, or we say that there is, this is our language, there is what is known as translational invariance. This is the meaning of translational invariance. Translational invariance. So this is a very common term that we are using. So the meaning is quite simple. That suppose that you have got a system, a simple system, and let me say that this is some origin O and some coordinate axis. Let me say for simplicity the Cartesian coordinate system, say some x, y, z, whatever it is. Okay, and I have got a system here. Okay, system of some dimension, right? Some n number of particles are there, right? And you can just describe the system with respect to this origin, right? Okay, so the system will have a Lagrangian, which will be a function of some qj's and qj dots in general, maybe possibly depending on time as well, right? Now, see, if I'm shifting the origin, from O to say that O dash. I'm shifting the origin of the coordinate system from O to O dash. Then, just if the Lagrangian of the system is not affected, by the shifting of this system, so means let me say that the new Lagrangian is L dash. The original Lagrangian with respect to O is L, and the new Lagrangian with respect to what? O dash is L dash. So if L dash is equal to L, means shifting the origin is not affecting the Lagrangian of the system, we will say that the system possesses what is known as translational invariance. You can try to understand what is the meaning. Translational invariance, because the Lagrangian is not affected by translating the system. You know, the shifting of origin means what? Just the system, either the system can remain there and the coordinate system can move, or the other way also, right? Okay, so by changing the coordinates of the system, if the Lagrangian of the system is not changing, we'll say that there is a translation. And when can it happen? You know that in this case, for this case to be true, that is the conclusion that L should be independent of the position coordinates, right? So L is independent of the position coordinate. Is not the conclusion? L should be independent of the position coordinates. Say in a Cartesian system, say it is independent of x, y, z. x1, y1, z1, x2, y2, z2 എത്ര വേണേലും എടുക്കാം നമുക്ക്. ഓക്കെ, ഇപ്പോൾ ഒറിജിൻ മാറുമ്പോൾ ലഗ്രാഞ്ചിയൻ മാറുന്നില്ല, അതിൻ്റെ അർത്ഥം എന്തായിരിക്കും? That particular Lagrangian should be independent of the position coordinate. അല്ലേ? എവിടെ വെച്ചാലും ലഗ്രാഞ്ചിയൻ വ്യത്യാസമില്ല. So it is independent of the position coordinate. What does it mean? You know that if the Lagrangian is independent, explicitly independent of certain coordinates, then those coordinates should be what? Means that these coordinates, position coordinates x, y, z, etc. should be named as what? Cyclic coordinate of the system, right? So they are cyclic coordinates. And what is the implication? What is the conclusion? The corresponding canonical momentum. That is the corresponding canonical momentum. അല്ലേ? Position coordinate corresponding ആയിട്ടുള്ള canonical momentum എന്ന് പറയുന്നത് എന്താണ്? That is nothing but the linear momentum. Okay, the corresponding canonical momentum. x, y, z ന് corresponding ആയിട്ടുള്ള canonical moment ഏതാണ്? x ന് corresponding ആയിട്ട് px ഉണ്ടാവും, y ക്ക് corresponding ആയിട്ട് py ഉണ്ടാവും, z ന് corresponding ആയിട്ട് അതിൻ്റെ z component of the linear momentum ഉണ്ടാവും, right? So corresponding canonical momenta, that is linear momenta p, അല്ലേ? px, py, pz. ഇത് ഒരു പാർട്ടിക്കിളിനാണെങ്കിൽ, രണ്ട് പാർട്ടിക്കുള്ള സിസ്റ്റം ആണെങ്കിൽ px1, py1, pz1, px2, py2, pz2 അങ്ങനെ വേണം എഴുതാം. Okay, so px, py, pz should be what? A constant of motion. That should be conserved. So this is our conclusion. എന്താണ്? Translational invariance. Our conclusion is quite simple. നിങ്ങൾ ഇതൊരു പക്ഷേ നേരത്തെ വേറെ എവിടെയെങ്കിലും പഠിച്ചിട്ടുണ്ടാവാം. Translational invariance. So this is a very critical concept. Translational invariance leads to ഒരു സിസ്റ്റത്തിൻ്റെ ട്രാൻസ്ലേഷൻ ഇൻവേരിയൻസ് leads to law of conservation of what? Linear momentum. So translational invariance of a system leads to conservation of linear momentum. Linear momentum. See, the thing is that translation motion linear momentum role play. So translational invariance leads to conservation of linear momentum, a very, very important conclusion in mechanics. Right? Okay? If the Lagrangian of the system is invariant when the origin of the coordinate system is changed, we say that there is a translation invariance. Means the Lagrangian should be independent of the position coordinates. So if the Lagrangian is independent of the position coordinates of the system, then you can conclude that directly. Without any doubt, you can conclude that the linear momentum of the system will be conserved. That is why I told you that knowledge of the cyclic coordinates of the system can give you a lot of information regarding the dynamics of the system. Similarly, I can just go to another thing. I think I can just predict the next one. See, similarly, the same manner, I can talk about another thing, what is known as isotropy of space. Isotropy of space. So these are the words that we are using. Isotropy of space. What is my isotropy of space? The properties of the system remains the same along any direction. We have said that the medium is isotropic. Isotropy means related to direction, same along any direction. Okay, whether you move to the left or right or top or bottom, okay, is not north or south, along any direction from a point, if the properties are remaining the same, we will say that the space is isotropic in nature, right? So the isotropy of space is otherwise known as rotational invariance. Rotational invariance. So rotation, it is related to angle, along any direction, if the properties remain the same. Rotational invariance. That's another terminology that is used. Okay, so isotropy of space leads to, I think I can make a prediction before me, leads to another conservation law. What will be that? So in this case, the Lagrangian will be independent of, so that is L is independent of angular coordinates, means angles, theta. Angular coordinates, I can say angular coordinates, say theta, some values of theta, right? L is independent of the angular coordinates theta. So if L is independent of angle, then angle is a cyclic coordinate. So when angle is a cyclic coordinate, what's happening? The conjugate momentum corresponding to angle is known as angular momentum, right? So isotropy of space leads to conservation of angular momentum. Conservation of angular momentum. So this is the second important conclusion that I want you to keep in your mind. Even though we do not discuss much about this one, this is some concept that I am leaving to you. So this is the second conclusion that you have to keep in mind. Similarly, there is a third important conclusion and a leading conservation law. Okay, that is known as invariance of translation in time. Okay, three invariances we are talking. Invariance under translations in time. Translation means change. Translations in time. What is the meaning? So if the system's property remains the same yesterday, today and tomorrow, so even though whatever be the time ahead or time back, so invariance under translation in time, t or t dash or t double prime, okay, the Lagrangian is what remaining constant. That's the meaning. Invariance under translations in time leads to yet another conservation law. What would be that conservation law? Okay, time is the coordinate here corresponding to position coordinate x, y, z. Okay, this is position coordinate. The conjugate momentum is linear momentum p is conserved. Correspond to the angular coordinate theta, the angular momentum L is conserved. So they are all conjugate pairs. Now it is the turn of time, and who is the conjugate momentum or conjugate variable of time? That is nothing but energy. Okay, so invariance under translations in time leads to conservation of energy. Conservation of energy. Okay, so that is just symmetry in that. I can just conclude it like, okay, symmetry in is not symmetry or invariance. Symmetry means invariance, right? Invariance in position leads to conservation of, this is a conclusion, final conclusion, conservation of linear momentum. Now, symmetry associated with rotational symmetry, right? Symmetry associated, or I can say invariance in space. Space means rotation, okay, or rotation. Rotational symmetry, I can say, right? This is translational symmetry. Translational symmetry. So translational symmetry in position leads to conservation of linear momentum. Similarly, rotational symmetry or isotropy of space leads to conservation of angular momentum. Angular momentum. And finally, what's the thing? The symmetry or invariance. Okay, invariance in time. Invariance with respect to translation in time leads to the law of conservation of what? Energy. And you know that these three conservation laws are the three fundamental conservation laws in mechanics. The law of conservation of energy, the law of conservation of linear momentum, and the law of conservation of angular momentum. Even though you talk about a large number of conservation laws in nuclear physics or particle physics, like law of conservation of other quantum numbers, like isospin quantum number and all those things. Okay, these are the three fundamental conservation laws in physics, and they are related to the corresponding symmetries. Okay, and I leave you for your additional reading. I leave you one article or one topic that is just available in the net. You can refer. It will be available in most of your classical mechanics textbooks. That is Noether's theorem. Noether's theorem. And this is something very important theorem related to symmetries and conservation laws. So it says that corresponding to every symmetry there is a hidden conservation law. That's a generalization of what I told now. Noether's theorem, given by physicist, much celebrated physicist M.E. Noether. It's good that you just refer to it at least. Okay, in this vacation time, you can refer to it and you can just get more concepts regarding it. Okay. That's an introductory lecture which is not a part of our syllabus directly mentioned. Okay, thank you.